One concept students really struggle with is significant figures and calculations with significant figures. So we really want to make sure that you spend some time on this and you really internalize it so that you can do it right throughout your coursework. This is not leaving you for Chem 1 or Chem 2, so make sure that you really get your sig figs down, okay? We have to remember that there are two sets of rules we're following. When we are doing multiplication division, we are keeping the least number of sig figs in our calculated answer. But when we're looking at addition and subtraction, we're keeping the least precise number as the limit to our sig figs. So however, the least precise or the least amount of precision in our measurement limits my overall sig figs. So let's look at the first example here. I have 4.932 times 39.47 minus 3.21. We do follow orders of operation here, okay? So there's no parentheses here. And so orders of operation, PEMDAS, that tells me I don't have any parentheses, none of that, no exponents happening, none of that, but I do have multiplication and I do have subtraction. The multiplication will happen first. So I'm gonna look and I say I have 1, 2, 3, 4 sig figs. And when I write SF, that just means sig figs. And then the 39.47, also 4 sig figs. So when I do the multiplication there, the answer, the numerical answer I get just from that, I'm not doing the 3.21 yet, but just from the 4.932 times 39.47, I get a numerical answer of 194.6604. Again, your calculator does not care about sig figs. It doesn't know what they are. It doesn't think they're important. You care because we care about precision within your measurements. We care about accuracy within your measurements. We can't make something more precise or more accurate than our least precise measurement, our least accurate measurement. So here, I'm going to keep this to 4 sig figs, 1, 2, 3, and 4. But I'm not going to round yet, because again, I don't want to create round off error. I do know though that I will cut the number here. Why do I emphasize that? Because now that 194.6604 is only precise to the first decimal place or the 10th position. I then take that and subtract 0.321. And what I get here in my calculator is 191.45604. But again, now I'm doing subtraction, so I'm looking at the precision of my measurements. This number is precise to the 10th position. I write it as 0.01. You can say the 10th position, whatever makes you most comfortable. I don't care. You know, it's not sorry, I'm trying to write point 0.1. It's accurate to that 10th position, the first decimal place. This is accurate to the 100th position, that second decimal place. The 1 is just a placeholder there. It's not saying that it's 0.1. It's saying that it's precise to that measurement. But that means that my final answer here is also only precise to that 10th position. This is my hundredths versus my tenths. My hundredths position may be more precise. I can't use that. So I need to cut the number so that I round it to end at that 10th position. Because the number I am rounding, the only number I look at is the first number to be removed. I don't care about the rest of the numbers. I care about that first number to be removed. If that first number removed is a 5 or greater, I round up. If it's a 4 or lower, I round down. Because it's a 5, I'm going to round this and I'm going to say 191.5 as my final answer. Excuse me. Let's go ahead and work another example. 5.982 times 0.00201. When I look at this number, 1, 2, 3, 4 sig figs. When I look at the next number, I have to remember my sig fig rules. Leading zeros are not significant. If you're unsure, put the number into scientific notation. If I put this number into scientific notation, I would have 2.01 times the negative 3. All of those leading zeros have disappeared. They are not significant. My number only has 3 sig figs. Captive zeros, meaning the zeros in the middle, captive zeros are significant. I do keep that. So overall, this has 3 sig figs to it. Calculate this out, and the calculator gives me a numerical answer of 0.01202382. Again, calculators don't care about sig figs. I know that my answer can only have 3 sig figs. I know leading zeros are not significant, so the 1 is my first sig fig. 1, 2, and 3. I'm going to draw the line right there. The first number to be removed is a 2, which is lower than 5. So I'm going to round down and I'm going to write 0.0120. Trailing zeros are significant if they come after a digit after a decimal place. This 0 is significant. It's telling me my number is precise to the 4th decimal place. So this number has 3 sig figs. The 1, the 2, and the 0 are my sig figs here. And that is my final answer. If I look at the example here, 4.953 plus 9.2 divided by 11.315. Remember the division symbol here acts like parentheses. What that implies, or what that means, is that I do this first, the numerator first, and then I divide by the denominator. So the 4.953 plus the 9.20 is my first calculation. I'm going to go ahead and plug that in the calculator, and I get 14.153. Again, that is my calculated answer. I haven't talked about sig figs yet. And that is divided by the 11.315. Now let's talk about your sig figs. In the 4.953, because I'm doing addition subtraction, I have to look at how precise my measurement is. This is precise to the 3rd decimal place. The 0 here is precise to the 2nd decimal place. My final answer can only be precise to the 2nd decimal place. I don't care about number of sig figs here, I care about precision of the measurement. My 2nd decimal place is here. My number can only be precise to there. But I don't want to round yet because I don't want to create round off error, right? Now that I'm going to do the division, now I'm going to look at my overall sig figs again. If my number is precise to the 2nd decimal place here, that means I have 1, 2, 3, 4 sig figs in my numerator, 1, 2, 3, 4, 5 sig figs in my denominator. I'm going to go ahead and plug that in my calculator, and I get 1.250817499. Again, that is a calculated answer. Calculators don't care about sig figs, but we do in class. 4 sig figs is less than 5, so my final answer is limited to 4 sig figs. 1, 2, 3, 4. I need to cut my answer right here. The first number removed is going to be an 8. So I need to round up, and I'm going to round this to 1.251 as my final answer. So I've done these 3 so far. Hopefully this makes sense. Hopefully this is what you're familiar with. If you're unsure, so we need to come ask for some help, okay? Or reread your sig fig rules. But let's continue our practice. You obtained a 5.68 gram sample of a compound for an experiment. A few minutes later, you obtained an additional 8.32 grams of the same compound. What is the total mass of the substance? Sometimes students have a hard time visualizing this. Let's just talk about what this means. Visually, let's say I've got a beaker, okay? And I went ahead and added some sample to the beaker. The sample I added originally to the beaker weighed 5.68 grams. After a few minutes, I go ahead and obtain more sample, and this time I have added 8.32 grams. I want to know the total mass here. The question itself is not difficult, but it is when you think about sig figs because students aren't thinking about it. They're just plugging in their calculator. If I just add 5.68 plus 8.32 into my calculator, it's going to tell me 14. But that is not the correct answer. The two ways to do this are either the way I do it is I just count my decimal places, or you can line up your numbers. What I mean by lining them up is writing 5.68, 8.32. When I add these up, I get 14, but I need my numbers to add up on the side. I have to put two zeros here so that I get the same number of sig figs. The other way to do it is to look, because I'm doing addition, I'm looking at precision of the measurements. Again, addition, subtraction. Ask yourself, how precise is my measurement? For multiplication division, you ask, how many sig figs? And for each one, you go with the least number. You go with the least precise measurement. You go with the least number of sig figs. Okay. So when I look at this one, I'm doing addition. So I'm asking myself, how precise? I here am precise to the second decimal place. Here as well, I'm precise to the second decimal place, which means my final answer must also be precise to the second decimal place. And then don't forget your units, because numbers are useless without units. What about the example down here? Let me move this up a little bit just to get out of the way. 8.672 times 10 negative 6 divided by 1.376 times 10 to the fourth. When I plug this in my calculator, I get 6.30232,558 times 10 to the negative 10. Okay, that is the calculated answer. When you are doing multiplication division, scientific notation is pretty straightforward. We're just looking for the number of sig figs. This number has 1, 2, 3, 4 sig figs. Remember, all that 10 to the 6th is doing is telling you how small the number is or how big the number is. In this case, what that's telling me is I have 0.000008672. Okay, that's all the 10 to the negative 6 is doing, is telling me how far out. 2, 3, 4. Yeah, I did. I'm checking to make sure I wrote the right number of zeros. It's checking to show me how, in this case, small the number is. And the 10 to the fourth here is just showing me how big the number is. This is saying the number is really 13760. Zeros are what get tricky, okay? In this case, this zero is not significant because there's no decimal place holding it in this place. It's just there. It's not significant. So by putting in scientific notation, it actually makes it easier to see it's not, in fact, significant. This also has 4 sig figs overall. So my final answer can only have 4 sig figs. 1, 2, 3, and 4. Cut my number here. I have 6.302. Don't forget this. This is part of your number. Times 10 to the negative 10. It is showing you how small that number actually is. But I had 4 sig figs in my numerator, 4 sig figs in my denominator. I'm doing division here, so my overall answer needs to have 4 sig figs as well, because that's the least number of sig figs I have. What about this one? I have 5.74 centimeters plus 0.823 centimeters plus 2.651 centimeters. Again, a lot of students want to line up their numbers, and that is perfectly acceptable to do. I don't care what your preference is. Lining them up is just visibly harder for me to do. I'm not great at lining up my numbers, which is why I do it by counting decimal places. But if I line them up, I'd have 5.74, 0.823, and 2.651. When you draw your line, you see that it's least precise to the second decimal place, okay? So when you add this up, you're going to get 9.214. This is what is significant. This is the number that's going to be dropped. You have to decide if you're rounding up or down. I just do it by counting decimal places. So this is precise to the second decimal place. This is precise to the third, and this is precise to the third. So the smallest precision is the second decimal place. Nine point 214, second decimal place. I'm going to round that to 9.21. What about the next example? I have 4.8 liters plus 3.965 liters. Again, you are welcome to line up your numbers. I know most students do better with that. That is perfectly fine. 4.8 liters and 3.965 liters. When I add these up, I get 8.765 liters. This is the first number that's being dropped because it's greater than it's 5 or greater. I'm rounding up, and I'm going to round this up to 8.8. Sorry if you're hearing all the noise. I have kittens and they want to be right near me because it's thundering out. 8.8 liters. Again, I just do it by counting decimal places. I have no preference what you choose, but this number is precise to the, or not just decimal places. I count the precision of the measurement. Let me clarify that. It doesn't have to have a decimal place. In these examples, they have decimal places. My 4.8 is precise to my first decimal place. My 3.965, sorry, I'm supposed to be doing subtraction here. I'm definitely doing addition here. I did addition over here. I'll do subtraction in a second. I just have to calculate the actual number. I don't know it, but I don't know it. I don't have it written down. Um, 4.8 minus 3.965. Let's see. Calculate that out quick. I get a new calculated answer of 0.835. But my 4.8 is precise to the first decimal place, whereas 3.965 is precise to the third decimal place. The first decimal place is the least precise measurement I have. So I'm going to round that first decimal place, give me an overall answer of 0.8. The number I'm dropping is a 3, so it gets rounded down and it just becomes 0.8. I'm not rounding this up to 0.9. And what I did over here, I just added them together. You can see it if I had added instead of subtracting them, same idea. If I had done it this way, I would still get 0.8 for the answer following my decimal places. I just didn't realize I had one part of my notes has it positive, one has it subtracting. Let's see, 5.02 nanometers times 89,665 nanometers times 0.1 nanometers. Because I'm doing multiplication here and here, I'm just looking at number of sig figs. I plug this in my calculator and I get 45,011.83 as my calculated answer. Here, I have overall 3 sig figs. Here, I have overall 5 sig figs. And here, I have overall 2 sig figs. That means my final answer can only have 2 sig figs, 1 and 2. So I'm going to cut my answer right here. I can write one of two things here. I can either just round it and say 45,000. Don't forget your units. I've got nanometers times nanometers times nanometers. That is nanometers cubed. Or some students are more comfortable writing some scientific notation. That is perfectly fine. 4.5 times 10 to the fourth nanometers. And don't forget they are cubed because I have nanometers times nanometers times nanometers, which gives me that nanometer cubed. Our next example here, 5.892 grams divided by 6.10 mils. When I calculate this in my calculator, my calculator tells me it's 0.9659016,393. It's a lot of numbers there. We'll deal with units in a sec. Lots of numbers going on here, okay? But I am doing division, which means I'm looking at how many sig figs do I have in each value. This value, overall 4 sig figs. This value, overall 3 sig figs. The least number of sig figs is 3. My final answer can only have 3 sig figs. So the 9, the 6, and the 5 leading zeros are not significant. Okay. But that means I need to cut my number here. The first number removed is a 9, so I have to round this up. I'm going to round this up to 0.966, but don't forget we had units in this one. So I have grams divided by mils. Gram divided by mil for my units. What's our next one? 2.526 divided by 3.1 plus 0.470 divided by 0.623 plus 80.705 divided by 0.4326. Okay, by orders of operation, when I have these separated like this is the same as saying this gets done, this gets done, this gets done. The division first, 'cause remember PEMDAS is multiplication, division before addition, subtraction. I'm going to do all those divisions, then I'm going to add the numbers together. So that's what I'm going to write over to the side. Okay, when I calculate out this number here, I get, let's see, I get a calculated answer of 0.814838797. I'm going to color code these. I'm going to add that to the next one. When I do this calculation here, I get a calculated answer 0.7544141254, or sorry, 1252. I can read my own writing. And when I do the calculation here, I get 186.5580213. Very rarely will you ever need to write out all these numbers, but I'm just trying to emphasize to you that your calculators do not care about sig figs. You guys are the ones that have to care. Let's go back through these a little bit slower now and actually look at the sig figs, because now that we have all the answers. So the first number here, the first calculation I did in blue, where I got the 0.8148387097 calculation. That came from right here, okay? When I look at the numerator, I have 1, 2, 3, 4 sig figs in my numerator and only 1, 2 sig figs in my denominator. What that means is I can only have 2 sig figs in my final answer. So this number will actually get cut here. I'm not rounding yet though, because again, I don't want to create round off error. But I know that this first calculation is only precise. Now I'm looking at addition. It's precise to my second decimal place. When I look at my second calculation, 0.470, trailing zeros after that decimal place are significant. So this has 3 sig figs to it. And the denominator, 0.623, also has 3 sig figs. So here, 1, 2, 3, this is precise to the thousandths place. Please don't judge my spelling. I'm not sure if that's right. And my third calculation, 80.705 divided by 0.4326, the 80.75 Captive zeros, meaning zeros trapped between two numbers, are significant. So this overall has 5 sig figs. 0.4326, leading zeros are not significant. They're just placeholders. This has 4 sig figs to it. So my final answer, 1, 2, 3, and 4, is precise to the tenths place. The first decimal place. When I add all of these numbers together, so I take these numbers here and I actually add them together in my calculator, I get a calculated answer of 188.1272741. But again, that is my calculated answer, okay? When I look at my numbers, hundredths place, thousandths place. Hundredths place is more precise than thousands, okay? But then I look here and I say tenths. This is the least precise measurement right here. The tenths place is my least precise, so that's going to control my answer. I'm only precise to my tenths place. I need to round my number right here, and my final answer will be 188.1. Now, a lot of the number examples we're doing in this section don't have units to them. In class, we'll almost always have units. But here, you don't have to worry about units. Nothing was listed with the question. Please pause the video if you want to write all of that work down because I need to erase it because it's kind of overwhelming for me to see the example below it with all of that in the way. So I'm going to shrink it, but it won't match up nicely anymore. Okay. Next example, 6.404 times 2.91 divided by 18.7 minus 17.1. Notice that they are intentionally in parentheses, and PEMDAS tells us we do parentheses first, which means I'm going to do this calculation and this calculation before I ever do the division. First thing I do though is I just plug them in the calculator. So I'm going to plug that numerator in the calculator and I'm going to get 18.63564. And I plug that denominator in the calculator, 18.7 minus 17.1, and I get an answer of 1.6. Now I'm going to look at sig figs. In my numerator, I am doing multiplication. So here I am going to look for number of sig figs. My final answer will have the least number of sig figs. 6.404 has 4 sig figs. Again, captive zeros, meaning zeros trapped between two numbers, are significant. 2.91 has 3 sig figs. So when I do the numerator, my answer here is my sig figs are here at 18.6. I'm not going to round yet, but I do know that I only have 3 sig figs in my numerator. My denominator, 18.7 minus 17.1, I'm looking for precision. I'm going for the least precise measurement. Tenths place or first decimal. Tenths place, first decimal, meaning that my answer here is only precise to the tenths place of that first decimal. So the actual answer from the calculator was correct for sig figs this time. My denominator only has 2 sig figs in it. I'm now going to complete the calculation. The 18.63564 divided by 1.62 gives me a calculated answer, 11.647275. But again, now I'm looking at division. I'm looking at number of sig figs. 3 versus 2, I have to go with the least number of sig figs. So I am going with 2 sig figs. My sig figs end at that ones position. The 11, the 1 of the 11, that second the second number 1 listed right there, that is my ones position, and that is the least precise I can make it because I need to have 2 sig figs in my overall answer. So I'm going to round, dropping the 6, Because it is a 6, I'm going to round up, and my final answer will be 12. Let's continue. I've got 9.5 centimeters plus 4.1 centimeters plus 2.8 centimeters plus 3.175 centimeters divided by 4. This is taking an average, okay? So first thing I'm going to do is I realize that, first of all, it's in parentheses, but second of all, when it's in the top of a division bar like that, it means you do that first, okay? So the 9.5 centimeters plus 4.1 centimeters plus 2.8 centimeters plus 3.715 centimeters gives me a calculated answer 19.575. But now I have to look at my sig figs. I am doing addition, so I'm looking at how precise my measurements are, and I'm picking the least precise measurement. This is precise to the tenths place, or first decimal place, tenths place, or first decimal place, tenths place, or first decimal place, and thousandths place, or third decimal place. My least precise measurement is to that tenths position, or my first decimal place. So my answer can only be precise to here. But again, don't want to create round off error. I'm not going to round until the end. I am dividing this overall value by 4, and I'll talk about that in just a sec. When I divide it by 4, I get an answer of 4.89375. Here's what's going to trip students up. This 4 does not count towards your sig figs. The 4 here is an exact number. So it's not going to limit your sig figs. Okay. And I know that really throws students off, but it is the definition of an exact number. It's like saying I have 24 students enrolled in my class. That is an exact number. It's not a measurement. Measurements have a sense of, or measurements always have a a piece of error to them. We're always estimating on a measurement. When I look at a clock, a regular clock, not a digital clock, but a regular clock, I am estimating where the minute's hand is. Okay. So I'm estimating my precision of my measurement. When I'm looking at a number of things, an exact number, such as this, having exactly 4 measurements, and I know it's 4 because it's a number of units, a number of centimeters, so number of measurements divided by one constant number divided by the number of them. That means an exact number. They do not limit sig figs. Okay, so not to further confuse you, but when I did that, I added these up, I saw 19.6 as my answer here. But now I'm dividing that by 4 to get to my final answer, okay? I divide it by 4 and I get a calculated answer of 4.89375. But I'm dealing with an average of measurements. I cannot make my final measurement more precise than my least precise measurement. So you've got to be careful with your sig figs here. We followed the rules properly, but at this point, this looks like it has 3 sig figs. But again, this is a summation of measurements looking for an average. My least precise measurements are all least precise to the tenths position. So my final answer is also limited to that same value. My final answer here will be 4.9 centimeters. I cannot make my measurement more precise than my least precise measurement. Okay, so we did follow the rules, but if I completely followed sig fig rules and didn't think about this logically, what these numbers meant, I would want to write 4.89. That's not going to give me the right number of decimal places though, because that would make the number more precise than these measurements here, which are the least precise of my measurements. What about this one here? 9.875 times 10 to the second minus 9.975 times 10 to the second divided by 9.875 times 10 to the second. Okay. They are put in scientific notation, which can make things more difficult. What do these really mean? You can plug this in your calculator. When they're in scientific notation and you're doing addition and subtraction, there's a couple tricks to it. You can watch the video on the tricks, or you can just take them out of scientific notation. And in this case, I recommend taking this out of scientific notation. The numbers are small, it's easier to do. watch the video. It's separate video from class that talks about doing scientific notation, addition, subtraction. I go through the tricks on that and how to do it when the numbers are really small, really big, a little more precise than this one. Or not, wrong word, I'm sorry. A little more clearly than what I'm going to do in here. In this video specifically, I'm going to tell you these numbers are not very big. Go ahead and take them out of scientific notation. It will make it easier for you to see it. So 9.875 times 10 to the second is the same as 987.5. 9.795 times 10 to the second is the same as 979.5. Again, the division line or that division bar means I do the numerator first. It's implying that these are in parentheses. Divided by the 9.875 times 10 to the second is the same as 987.5. This is how you check percent error. That's what this calculation is. You're comparing something to its known value. And so when I take the numerator, the 987.5 minus the 979.5, numerically, I get an answer of 8. Okay, so again, what I did was the subtraction here. I'll deal with the units in a sec. I just get a numerical answer of 8. But notice that this number is precise to the first decimal place, as is this number, which means I need to write zero point 0. How do I know to put a 0? Because I have to have a number there. This number is precise to the first decimal place. I don't have a numerical value there, so I need to use a 0 as a placeholder. 8.0 divided by that 987.5. This is in kilograms times 100%. Now I'm doing division, so now I'm looking at the number of sig figs. My numerator, both of these numbers are significant. So I have 2 sig figs in my numerator. By denominator, there is a decimal place right there. It's just not, well, it's kind of hidden in there. 987.5 has 4 sig figs. When I calculate this out, multiplied by 100, the 100 is exact. It does not limit my sig figs. Okay. I get a calculated answer, 0.008101268. It's a little excessive. Sorry, times 100. So do the number first, then I wrote it down times the 100. So, same, if I do it times 100, I would have a number of 0.8101268. Let's think about our sig figs. My numerator has 2 sig figs after the subtraction. My denominator has 4. That means that my number is precise to the second decimal place here because that's where my sig figs are. I don't have any numbers before the decimal places. I need 2 sig figs. So my final answer will be 0.81, but don't forget your units. My kilograms have canceled out, but now my unit is percent. I do have a percent here. And to finish it off, just 2 more calculations, but looking at temperature conversions with sig figs. Convert 43 degrees Celsius to Kelvin. You guys do need to know the conversion for between Celsius and Kelvin. Remember the conversion from degree C to Kelvin is adding 273.15. If you're going from Kelvin to degree C, you're subtracting that value. I have 43 degrees C plus 273.15. This gives me a numerical answer of 316.15. My sig figs here, this is precise to the ones position. So I can keep my answer here to the ones position. So my final answer is 316, and I'm not going to forget my units. I'm going to go ahead and write a K there for Kelvin. And the last question in this section, the boiling point of liquid nitrogen is negative 196 degrees Celsius. What is the temperature on the Kelvin scale? Again, if I'm going from Kelvin to degree C, I am subtracting 273.15. Okay? So I've got a Kelvin temperature. Oh, I am trying to go to Kelvin. Sorry, I'm tired. It's late, and I should pay attention to what I'm doing. So I'm doing the same thing as before. I'm adding it. And this time, though, starting with negative 196 degrees C. I'm still adding 273.15, because again, this is if I was going from Kelvin to degree C. I am going degree C to Kelvin. So I'm adding 273.15. Negative 196 plus 273.15. Students want to miss that negative. It is important. You have to plug it in your calculator. Okay. It is a negative temperature. That doesn't mean it's a negative number. It just means it's below zero. It's really cold. Negative 196. It does have a decimal place shown there. It doesn't much matter if the decimal place is there. The decimal places are really important if you have zeros. When they're integers, they're always significant. When I calculate this out, I get 77.15. Notice though, what are my sig figs? This is precise to the ones position. This is precise to the hundredths. My final answer can only be precise to the ones position. So my final answer will just be 77K or 77 Kelvin.